So in the previous videos, we have already discussed about the variation or the thermodynamics of the Bose-Einstein gases, and we already plotted the corresponding plots for the variation of the specific heat with temperature and also the number of particles with the temperature for Bose-Einstein gases. Here in this video, we will be discussing about the variation of the pressure of the Bose-Einstein gas with temperature. We have already made some we have already made some inverts into that plot, and we have already written that P by Kt is equal to 1 by lambda cube G of phi by 2 Z. So this was the general situation, and so this was our equation 11 previously, and we know that as Z tends to 1 in the Bose-Einstein system, we can write the expression for P by Kt is equal to 1 by lambda cube zeta of phi by 2. This was expression 25. So these two expressions we have already written. So what does this equation, for example, both these expressions we take, we know that for lower temperatures, for example, here in this expression, zeta of phi by 2 is a numerical value, is a fixed value, right? This means that my P, right? P is now will be proportional to T raised to phi by 2. Why? Because I have lambda cube here, which means that this will be T raised to 3 by 2, and then we have this T also coming to the numerator. So therefore total T raised to phi by 2. So P is directly proportional to T raised to phi by 2. If we just take the case of equation 25, that means at lower temperatures, this graph should obey P at P proportional to P proportional to T raised to phi by 2. Now what happens at transition temperature? We were talking about the transition temperature, right? Transition temperature Tc. This is the temperature, transition temperature, or the critical temperature in which the system will start showing the Bose-Einstein condensation. We have plotted both the graph of CV and also that of the N, and we have considered the situation of Tc, the critical temperature, in the case of Bose-Einstein gases. So there, if we can write the expression for P by just using this expression, zeta of phi by 2 at Tc. Tc is anyway low temperature, so therefore I can write P is equal to K Tc raised to phi by 2. I'm just releasing the value of lambda cube, right? So therefore I have to express it 2 pi m by s squared raised to 3 by 2 zeta of phi by 2. Okay. Now we have already derived one expression for Tc previously. What was that expression? I have mentioned about that expression, or we have derived that expression in one of the previous videos. The expression was Tc is equal to h squared by 2 pi m k n by v theta 3 by 2 raised to 2 by 3. So this was the expression, and that was equation number 29 previously. So if I apply equation 29 into equation 33, I will get the expression as P at Tc is equal to theta of 5 by 2 divided by theta of 3 by 2 n by v k Tc. So theta of 5 by 2 by theta of 3 by 2. Both are numerical values, which is the values are readily available. And if we just substitute for them, I will get 0.5134 theta of 5 by 2 by theta of 3 by 2 into n by v k Tc. So basically this expression 34, what does it show? What is the significance of that? It shows that at Tc, the value of my pressure will be half or nearly half of the value of the pressure for the classical gas. We know the expression for a Maxwell-Boltzmann gas, PV by NKT. PV is equal to NKT, right? So that is the classical case. So what does this tell? This is telling that my pressure at Tc will be half of that value. So this is a very useful information when we plot the graph of pressure versus temperature. Now what is the region we need? Input we need for our plot? T greater than Tc. What happens? So at T greater than Tc, I know the expression. I have to take care of this expression, g of, where was that? Yeah, g of 5 by 2 is Z. This is a very general expression, which I know that P is equal to NKT by V, g of 5 by 2 is Z divided by g of 3 by 2 is Z. Basically, we have, in order to make such a ratio, what we have done is that we have substituted for lambda cube from the equation of n by v. N by v is equal to 1 by lambda cube g 3 by 2 is Z, and we have used that expression over here so that we get this expression. Right, 1 by lambda cube, and we have the n by v is equal to 1 by lambda cube g of 3 by 2 is Z. So if I now take the expression for 1 by lambda cube is equal to n by v into 1 by g of 3 by 2 is Z. But P is equal to 1 by lambda cube g of 5 by 2 is Z. Instead of this 1 by lambda cube, I give this expression. So on substitution, I will get such a expression. So that is how I have done that. And so this is the graph which will decide the intermediate region just above the Tc. So when T is much greater than Tc, what happens is that we have the virial expansion coming into picture. We have already written that expression previously, that PV by NKT is equal to sum over L is equal to 1 to infinity AL lambda cube by small v raised to L minus 1. And we already discussed that this expression, if we allow this expression to play out, this expression will drive into a situation which will make your left hand side approaching the classical value in an asymptotic manner. We have already discussed this thing when we were discussing about the CV plot. So similar situation happens in this situation also. So combining all those things, we can now try to plot a graph. Okay. So let's try to do it in this figure. So we have PV by NKT in the y-axis and T by TC in the x-axis. First and foremost, I can always imagine that there is a classical value. So let me put this classical value. What is classical value? PV is equal to NKT. So this has to be a proportional graph like this. And let me note this as the classical. This is a classical line. Now what happens? I have now I have regime which is less than Tc, or at lower temperatures. We already concluded that this is going to obey like T raised to 5 by 2. Right? At lower temperatures, T is directly proportional to T raised to 5 by 2, and therefore I will have a graph of that. But there is one more condition which we already discussed, that at T is equal to Tc, my Bose-Einstein pressure temperature graph will be half of the classical value. So let's take, this is my T is equal to Tc. Okay. T is equal to Tc means then in the x-axis I have the 1 over there. So that means then it will be half of this one. That means I will put a cross here. At T is equal to Tc, it will be half of the y value. Right. So, and then I have to plot a graph of T raised to 5 by 2. Yeah, something like this. And this is actually my Bose-Einstein T raised to 5 by 2 line. This is the behavior which happens at low temperature. But what happens is that after Tc, actually it does not behave like that. It actually is supposed to be asymptotically approaching the classical line. Therefore, my graph after Tc will be something like this. Something like this. Asymptotic to classical. The blue line. So this is how my ultimate graph will look like. So it will be like this. So this is the for the PV by NKT for the Bose-Einstein gases. Okay, so that's it. We'll move the rest of the things in the next video.